For the longest time, medical implants have been pretty straightforward. You lose a piece of bone, you get a piece of metal to replace it. Simple. But what if an implant could be more than just a spare part? What if you could actually become a living, breathing piece of your own body? Well, let's get into how scientists are literally turning inert metal into living tissue. So, our story kicks off with a massive problem. Just look at this scan. That whole highlighted area, that's a huge tumor in the sacropelvic region, which is, one of the most complicated bits of our entire skeleton. Taking that tumor out means removing a critical chunk of bone. And your standard off-the-shelf implants, they just can't do the job here. No way. They won't fit right, they won't be stable, and they definitely won't bring back proper function. And that leads to the big question, the one that's driving all this incredible innovation. When a part of your body is this unique, this complex, how on earth do you even begin to replace it? The first breakthrough didn't come from biology, actually. It came from pure engineering. The initial challenge was all about getting a perfect custom fit. And this process is just brilliant. It all starts with these super high-resolution scans of the patient, which create a perfect digital blueprint. Then, surgeons can 3D print cutting guides that are custom-made for that person's anatomy, so the removal is incredibly precise. And finally, using some amazing tech like additive manufacturing, they create an implant that is an exact mirror image of the bone that was lost. So, that problem of getting a perfect fit, solved. But here's the twist. This perfect engineering solution actually created a brand new and pretty dangerous biological problem. It turns out the implant's greatest strength, its incredible toughness, was also its biggest weakness. And when you look at the numbers, the difference is just wild. Solid titanium has a stiffness of about 110 gigapascals. Our own bone? It's down around 15 to 20. That means the implant is nearly 7 times stiffer than the very bone it's supposed to be helping. And that has a huge effect on the body. See, on the left, that's what happens with one of these super stiff implants. It takes on all the stress, all the load, and the bone around it, it basically thinks, hey, I'm not needed anymore, and it starts to waste away. That's the complete opposite of what you see on the right. Healthy bone is always remodeling and rebuilding itself in response to everyday stress. This whole phenomenon has a name. It's called stress shielding. And here's the key takeaway. Our bones need stress to stay strong. It's a use it or lose it situation. By shielding the bone from that work, the perfectly strong implant was actually making the skeleton around it weaker, which could cause the whole thing to loosen and fail down the road. Okay, so to fix this, the engineers had to completely change their thinking. They needed to stop thinking like builders and start thinking more like gardeners. They had to create something that bone could grow into, not just something it could bolt onto. And the solution is beautiful when you zoom way in. Instead of a solid chunk of metal, the implant is designed to be a porous scaffold, kind of like a metal sponge. This complex web-like structure is the key to solving that stiffness problem and actually inviting the body to move in. And the design is incredibly precise. The overall stiffness, what they call the elastic modulus, is tuned to perfectly match our bone, which gets rid of that stress shielding problem. The pores themselves are engineered to be between 100 and 600 micrometers. That's the sweet spot, the perfect size for bone cells to crawl inside and start building a new home. And it's all interconnected, creating tiny channels for blood and nutrients to flow deep inside, making sure that bond is strong and alive. But of course, there is another problem. Even with this perfect architecture, they hit a new wall. The surface of the titanium, while it's safe for the body, is what's called bio-inert. It's basically a stranger. So healing is slow. You can see on the left the cells are really struggling to get a grip. And even worse, that passive surface is the perfect place for bacteria to set up camp, making infection a huge risk. This is where the story gets really exciting. The solution was to give up on the idea of a passive scaffold and instead make the implant an active player in its own healing process by giving it a kind of living, bioactive skin. The idea is to tweak the surface so it can actually direct the healing process and even defend itself. So instead of just sitting there passively, the implant starts sending out signals, talking to the body's cells in their own chemical language. And one of the coolest ways they do this is by embedding the surface with specific mineral ions. Take zinc, for instance. The cells that build our bones, osteoblasts, they respond directly to zinc ions. It's like a chemical green light that tells them, okay, time to get to work and start growing. And how well does this chemical green light work? The data is pretty amazing. Adding zinc to the implant's surface can boost the growth of these critical bone-building cells by a full 25%. And it doesn't stop there. It also increases cell adhesion. That's the ability of those cells to physically latch on and form a rock-solid bond by a massive 40%. But what about that other huge problem, infection? Well, this bioactive skin can be designed to fight back. By mixing in other types of ions, you can create a surface that is absolutely lethal to bacteria. And the results are just staggering. By using an ion like copper, the implant can wipe out 99.45% of SRES and over 98% of E. coli, two of the most dangerous bacteria you can get in a surgical infection. The implant is now actively defending itself. And this might be the most incredible part. These advanced surfaces can actually have a conversation with our own immune system. See, the body's normal reaction to a foreign object is to attack it and wall it off, which leads to failure. But a bioactive surface can actually flip the immune response from attack mode to repair mode. It convinces the body to treat the implant not as an invader, but as a partner in the healing process. So when you put all of this together, what do you have? We're watching a fundamental change in what an implant even is. It's no longer a static piece of metal. It's becoming a dynamic, living organ. It really is like a symphony of design. At the macro scale, you've got that perfect anatomical fit. At the mesoscale, you have the porous architecture that creates biomechanical harmony. Zoom into the micro scale, and you have bioactive signals that encourage growth and fight off infection. And now, at the nanoscale, we're starting to see real, responsive functions. And the next generation is already on its way. We're talking about smart implants that use incredible materials like graphene that can actually respond to things like light or electricity to release drugs exactly when they're needed, or even adjust cell activity in real time. And all of this leaves us with a really powerful idea to wrap up. The goal isn't just to replace what was lost anymore. The ultimate goal is to create a living, integrated system, one that heals, defends, and adapts, becoming a true, permanent part of the body.